All right, we're going to take our next step now. Things are a little bit different, but we're not going to use any tools that we haven't already acquired. We're just going to apply them to different things different ways. So we're going to look at the general category of what's called structures. We're going to look at three different types of structures in order here over the next 3 days. The first is what's called trusses. And by the way, from now on, we're talking about the types of things that you're going to want to do for your final report. There's a final report required for this class. We'll talk about it in a few days so you can start preparing for it. But start thinking about the types of things you want to do. These structures, what we've looked at so far when we looked at structures, and we've looked at lots of structures as we've gone through the class, what we've looked at so far is just what are the external forces. So if there's maybe some kind of guy wire there to stabilize this structure, maybe there's some kind of weight on the structure there that is pulling on and causes some forces. We then need to figure out what the reaction forces were at the base. That's the type of thing we've done so far, is just look at these external structures, external forces. Now we're going to look at forces that are interior to these structures, and we'll start with trusses, which are structures made of exclusively two force members. Remember what those are? Two force members. What was the deal with those, other than there's two forces?
Are they coherent? No.
Two force members are any members who have only the two forces in them, which means they must be pinned at each end, and no more than pinned. So if we're looking at some kind of bridge structure, each of the joint intersections are just simple pins. It means we're also not taking into account what property of most objects?
Mass.
The mass. Well, it's not so much that we don't care about them. We don't care about the weight of any of these, which generally means they're massless, because most of these are earthbound structures of some kind. If we took into account the mass or the weight, that would be a third force on each one of those members, and then we would not be talking about what we call a truss. Also, if you look at any bridge, you'll see another characteristic of all of those structures, those real-life structures, that's different than the pin joints that we're looking at. Most of those have what are called gussets. You'll see a big plate over there with rivets all over the thing, maybe welded as well. That makes it not a two-force member, of course, because that kind of thing can support a moment reaction at the joint where none of our pin joints can support any moment. Remember, the deal with the pin joints is they're free to rotate as needed. That's not the case when there's some big plate fastened over those. So if you look at any bridge structures or even a truss up in your attic or in your garage, you're going to see those very same plates at each one of the joints. What that does for us is it means the solutions we're going to find for these, and what we're going to look for is the forces at each of the joints on the pins, and thus the forces as well in the members themselves. What that does for us, the fact that we keep these as pinned joints, means that we're coming up with a very, very conservative design. We're going to come up with a design that really can't support a whole lot of force, such that when it's built in real life, it's going to be way overbuilt and have a huge factor of safety in it. We're also going to stick to planar trusses, which are 2D trusses. Well, no, we'll do a little bit with space trusses, but most of what we'll do will be planar trusses as we go through here. We're also going to look at frames, and we'll do this on Monday. Frames are trusses with at least one 3/4 member or more, 3 or more forces. At least one. There might be more, and there might be members with 4 forces. And that first structure I drew there is an example of this upright has 1, 2, 3, 4, 5 forces in it. So we could do a problem like that as a frame problem. And most of those will also be 2D planar. This diagonal piece, is that a 2-force member or not? If the joints are pinned, yeah, that's a 2-force member. There's only 2 places any force could be applied to it. We don't count the XY components of a force as 2 different forces, because we can resolve those into a single force. So there's only a force at this end and a force at that end. What about the horizontal piece? How many forces there? 3, assuming again these are pinned joints. 1 there, and 1 there, where the load is. And then on Wednesday, we'll hit the last of the type of structures we're going to look at, and that's what we call the class of machines. These are frames with movable parts, in that the point of a machine is that some of the members actually move, as in pliers or tire jacks or those kind of things. Frames with movable members. And so we'll hit those in the next couple days. All right, so that's the setup for this general discussion of structures. All right, so let's now look at the analysis of a simple truss. Simple truss means planar with pinned joints. All right, we're going to have 2 different ways to analyze these. And I reserve the right on the exam to specify a particular method. We'll talk about why one method might be preferable over the other. And so if I don't specify, then you have your choice of which method. But there's 2 methods that we're going to use. The first we'll go through is what's called the method of joints. That's the one we'll do today. The second is called the method of sections. And we'll do that on Monday. Method of joints is fairly straightforward. The biggest challenge in it really is just keeping things straight, just paying attention to what's going on and not making extra assumptions that aren't required, those type of things. Again, what we're looking for is the force at each of the joints, because that's the force in each of the members of the truss. So ultimately, that's what we're looking at. So first thing we're going to need is a free body diagram. We're going to actually use several free body diagrams, but the first is generally of the entire structure. It's possible, I guess, we could have a problem where we don't need to do this, but that's just because there's so much stuff given. You don't need to make this step to get the things that aren't given, usually, no problem. Free body diagram of the entire structure. What this is going to do for us is it will find the reaction forces. Remember, those are the forces that support the structure to keep it from accelerating, doing whatever it's not supposed to do in this class. Usually the best way to find that is by a free body diagram of the entire structure. And then the usual tools that we have apply. We'll sum the forces and the moments and make sure that there's zero. Just like we've done before. We've already done this for these type of things. What we haven't done, though, is the next step that really allows us to analyze these trusses. We'll do then a free body diagram of each joint itself. By the time we've done a free body diagram and an analysis of each joint, we'll have the entire structure. We'll find the forces on the joint, and we're going to step through all this, of course, in a second, just kind of laying out the game plan. We'll find out the forces on the joint, which then, of course, are also the forces that are in the members that connect to that joint. So if we happen to have a joint like that, and of course there's more of the structure there, but I'm just looking at a particular joint. If we have a joint like that, we, well, of course, typically have things labeled. So that's just for reference sake. So if we have different, each of the joints labeled, then we'll do a free body diagram of the joint itself. So we'll take point A there and draw in any forces that are on that joint. Well, we've got something hanging from it, so we're certainly going to have that in the problem. There must be other forces on that joint, otherwise it wouldn't be in equilibrium. We also know that only two force members are connected to that joint. That's one of the characteristics of a truss. What's that mean to us then? If only two force members are connected to that joint, what does that tell us about the other forces on that joint? Let's remember. Two force member with two forces on it, one at each end. It doesn't have to be at each end, it could be somewhere else, but it's only two forces. What's true about those two forces?
Equal and opposite.
They're equal and opposite. Maybe it'll be like that, maybe they'll be the other direction, but they'll be equal size and opposite in direction. Otherwise, we couldn't possibly solve a force balance on a two-force member. There's no other way. That means to us that the forces always lie along the line connecting the two adjacent joints. That's good for us because we know then the forces involved there. We know there's one force that's going to go from A to B. We might not know whether it's pushing on the joint A or pulling on the joint A. It could do either. But we do know its angle. It's got to have the same angle as the member itself. At least the line connecting the two joints. If the member happens to curve, doesn't matter to us. And so we have another one that's going to be in that direction because that's where the next joint lies. Once we've got that much, we can even determine the general sense of them. If I have no other forces involved, and I've got one down force, I better have some up force. The only other place that could come is here, so I know for a fact that joint must go that way. Since I now have some right pulling force, I need some left pulling force, I know that joint must go that way. That helps a lot. It just eliminates minus signs. If I don't know what the sense is, then you take a guess, and if you guessed wrong, you get a minus sign in your answer. But doing this way, I can actually eliminate any minus signs from anything I'm trying to do here. The other thing that's important for us to realize is once we know what the forces are, let me do it this way. Once we know what the forces are on a joint, we know what the forces are on the member that connects to that joint. Let me just give myself a little room here. So that's the member AB then. And we now know what forces are on it. If it's pulling on joint A, then what's joint A doing to that member? If the member is pulling on point A, which it must do to exert that kind of force, then point A, joint A, must be pulling back as a reaction, equal and opposite reactions. So we know that now the force in member AB must be something like that. And you can look at that and see that that then is in tension because it's being stretched. The other member, I think I call that AC, must have forces like that, and it's in compression. We need to know that because that's part of the design of each of the members when we get to that. You can do very different things designing a member that's in tension and other things to one that's in compression. In real life, it's certainly possible that members in a real structure might alternate between compression and tension as the load changes. When a big truck drives across a bridge, that's a very dynamic load. An awful lot of things are happening that certain members in the structure might alternate between tension and compression as the part goes over. But we're doing static problems where we don't have objects actually in the process of crossing the bridges or loads in the roofs, trusses changing, or any of those type of things that we have to worry about. So, in general, perhaps an easy thing to do is anytime there's a force and you don't know the direction of it, and you have to just take a guess, and we'll see some of those coming up in the sample problems. Go ahead and guess that it's in tension, so that when you solve for it, if it's positive, you're right, it's in tension. If you're wrong, it's negative, then it's in compression. And we can use that as sort of a guideline. Some books actually say make every force in tension, and then it automatically shakes out whether they're in tension or compression. But it's going to do that anyway, I think. So I prefer starting out a little bit more realistically and going from there. All right, so time for a problem. Let's set up a problem. To keep things simple for us, I'm not going to draw the members in that way. I'm just going to draw a straight line to represent a member, just to keep things a little bit simpler for us. So we have a very simple three triangles in the structure. Why triangles? That's not just a coincidence. It's not just something I happen to pick for this problem. Why triangles? No, because in an equilateral triangle you're more likely to have that, but that's not necessarily the case. But why triangles? And if you go out and look at antenna towers, cell phone towers, or the truss up in the roof of your garage, it's nothing but triangles. Mr. Raptor?
It's more structurally sound.
It's much more structurally sound. A triangle, no matter what the load's on it, as long as there's not material failure, and in this class, none of these materials will fail. Come spring, that's what we're going to look at, the possibility of these materials actually failing under these loads. We're going to assume now that whatever the materials, whether it's a wood truss or a steel truss, doesn't matter. There will not material failure, but a triangle will not collapse. If we had part of a truss that looked like that, remember the joints are freely pinned and they can turn, which means that this could collapse and then the structure itself would fail even if there's no material failure. So we can't have any squares or shapes beyond that, polygons, any polygons above a triangle. That doesn't mean we don't have some design options as we go through this. So we've got this structure and it's pinned in support at one corner. Has a roller support at the other corner. Very same type of thing we were doing with those simply loaded beams. We have to have one support that only has one force in it. Otherwise, there's too many forces in the problem for us to solve. We'll be able to solve those problems later, next term, just not now. And then there's two loads on this from whatever source. Maybe there's another story in the building above. And each, this is in pounds and all the measurements will be in foots. Okay, so there's the basic setup. Label the pieces for reference so we're all talking about the same thing. A, B, C, D, and E. There'll rarely be a joint F because F means force. So if you need that in the problem, we reserve it for that case. All right, so the dimensions in foots, 12 feet between those two top parts, 12 feet across the bottom part there, and then it's a symmetric design, so it's the same on one side as is the other. This is 6 feet, and the height of the whole thing is 8 feet. And we want to analyze the forces in each of the members. It's possible that we can make some design decisions when we know that. First step. First step, look at where I listed the steps. What did I say?
Free body diagram?
Yeah, free body diagram of
Whole structure.
entire structure, because we need to find out what these reaction forces are because that's what the forces, that's going to determine the forces in each of the members. So we'll keep it simple. We don't need the different members for the overall free body diagram to find the structures, to find the reactions. We do care where each of the forces are, because as you know, that certainly depends upon what the moments on the structure are. So what are the reaction forces on this? Some reaction force at C and some reaction force at E. But what? This is a pin supported joint up here. And so what are the type of forces that a pin support can exert? Remember that the attachment itself is securely mounted on something, maybe a cliff or another building or something. So what do I take out that support and I put in its reactions. What do I put?
Force in the X and Y direction.
Generally a force in the X and Y direction. Maybe we can determine something about the sense of those. Maybe we can't, so it doesn't really matter, because if we're wrong, we'll get a minus sign, as simple as that. So we'll call that CY and CX. What about at E?
Just an output force.
Because of the rollers, there's no transverse support. There's only the support there, so we don't even have to call it EX and EY. It's just going to be E. And we can figure out what those are. Who wants to do CX? Just by inspection, we know CX has got to be 0. It's not truly inspection. All you're doing in your head is summing the forces in the X direction. That's the only one. It must be 0. And so then we can solve for the other forces. I'll put them down just so we hopefully we don't need to step through this. We need to look at the other parts of it that are to come. So E turns out to be 10,000 pounds. And CY turns out to be minus 7,000 pounds. Meaning, yeah, we just guessed wrong on which way it's going. All right, that's nothing more than you could have done for a couple weeks anyway. You got to sum the forces in the Y direction. Then you've got to do the moments about one point or the other, and you'll get all the forces that way and get those reaction forces. So double check, make sure I know how to do that, because I'm not going to give you that on a test. We just need to move on to the other stuff in this problem. All right, so now we've got this structure. With known loads. 2,000 there. And as the drawing gets a little more crowded, I'll leave off the units because we know what they are. It's pounds and feet. 1,000 there. We know. Now, you have the option now of turning CY around and getting rid of the minus sign, but you don't have to. But if you keep the minus sign, you've got to keep that direction because that's where it came from. Personally, I just soon turn it around and get rid of the minus sign. So I've got 7,000 there, and then the 10,000 there. And now we want to analyze that using the method of joints. We can start anywhere, but if you start somewhere with fewer unknowns and more knowns, you just have less to do to get going. Oh, let me label them. A, B, C, D, and E. And we actually don't need the dimensions anymore. They're not part of the problem. They were certainly part of this part, but for doing the joints, we don't need them. So notice that at joint A, we have two unknowns. We don't know how much force is coming from that member. We don't know how much from this member. And we have one known. Joint D, three unknowns, no knowns. So we certainly don't want to start there. B, one known, 1, 2, 3, 4 unknowns. So we definitely don't want to start with that one, and so on. So we can either start at C or at A. It doesn't matter which. Both have two unknowns and one known, so it's 6 of one, half dozen of another. So we'll start at A, just because it's nearest to the drawing as I start putting these in. I know it's got the 2,000-pound load. I know there must be a force coming from the member that connects it to B. So I'll just draw that line. I won't put the arrowhead on yet. Maybe I can get that before I go any farther. And I know that there must be a force lined up with the member going down to B. D. And by the way, from the dimensions, it turns out that this is 53.1 degrees. We're going to need that, obviously, because now we need to sum the forces in the different directions. All right, let's see. Let's call this just AB, and we'll call this force AD. We don't need to put an F on those, because that's all we're talking about is forces. So we'll save ourselves a little trouble. Do we know which way those are going? If we don't, we'll just guess. But if we do, let's put it in and avoid any minus signs if possible. Which is which?
AD is going towards A.
I've got some down force. That's the only place I'm going to get some up force, so I know it's got to go that way.
And AB is going away.
And then that tells me AB has to be going like that. And so now I can solve for those by simply summing the forces. In the X direction, summing the forces in the Y direction. We're lucky. We have two unknowns, there's two equations, we should be able to solve the problem, at least solve that joint. What about using a moment equation?
No need to go to point A.
They'd all be zero.
Okay.
Well,
There is no moment in this little sub-problem we have here. All forces go through the same point. None of them exert any moment. It's no use going over to some other point because that just complicates things. I guess we could do that. We can sum the moment about any point, even if it's somewhere else. But it's sufficient to do this, and we don't need to do anything more. Notice that for those joints where there are more unknowns than we have equations, it's not a big deal. Once we've solved this joint, we'll know the force coming in there. There's one less unknown. We can go solve this joint directly. We'll know that force coming in. That's one less unknown. We're down to two unknowns at that joint. So the solution has to progress through the structure as we go. All right. I don't think we need to do those because that's just an algebra problem now. So I'll give you each of those. Where are they? AD is 2500 AB is 1500. Read that right? Yeah. And that just comes, again, from solving the two force balances in the two different directions. Now, here's my recommendation. It's purely a style thing, just to help keep things straight. My recommendation is that as you go to the different joints, keep them about where they fall in the structure. You're just less likely to make a mistake then. So I know that D is down here somewhere. We know that over here somewhere. So it's kind of like an exploded picture of the thing as we go. So B now has three unknowns. We know one of the members, we don't know the other three. So there's no sense us going to B. We just can't solve it. We only have two equations. That's all we've got for these joints problems, is these two equations. So we can't do more than two unknowns. Could we do D? Can we do D now? Should we go to it next? We can skip over and go to C and start working in, but could we do D now? I have a yes, I have a couple no's, I have a couple, I'm not going to even look them in the eyes. Fiona, think we can?
Yep.
We can't have more than two unknowns. Every member exerts a force. We already know this force. We just got it. How do I draw it at point D? I know the angle of it. Do I know the magnitude of it? It's 2500. Do I know the direction of it? It's equal and opposite to this one, because remember, these are the forces coming from the member that's connecting them, and that has equal and opposite forces. So we've got that. Is AD in tension or in compression?
Tension.
Well, we have a 50-50 chance of guessing. Is member AD in tension or compression? Not both. You save that kind of attitude for the election. This is serious. We got to get it right. Is the member AD in tension or compression? If we're not sure, remember, these are the forces by that member on the joint. So we could draw the member itself and put not these forces, but equal and opposite to those forces. And then you've got the picture. It's got to be like that. That member's in compression. Now, that's important to us, because one thing we could decide anywhere along the structure, if we were the designers of it, is if we have a member in tension, maybe we can take it out and put in a cable. Be a lot lighter, might be a lot cheaper, and if it's only going to be in tension, a cable can take tension. A cable cannot take compression. So we wouldn't want to put a cable in here and stand under this thing. You might want your boss to stand under it, but you don't want them. A couple other forces, maybe we know their direction, maybe we don't. Let me move this so it's not conflicting with the other ones we've got here. Do we know what direction those are? We know what angle they are. Do we know what direction they're pointing? If not, we'll just guess. But if we do, let's make an assessment. We know this one's coming down. This one's got to go up. And since that's one going to the right, that one must go to the left. And we can label these. This is DD, and that one's DE. And we can solve for those two. Comes out to be, this one's also 2,500 pounds, and DE is 3,000. Now, can we do joint B?
Yes.
We can either go up to B, and again, my recommendation is draw the joints as you solve them about where they lay, at least in the same spatial organization. You're just less likely to make a mistake. It's much easier to transfer the force that you found down here on joint D up to joint B where it next acts if you draw it this way. Much less likely to make a mistake. Do we know anything about the force coming out of B? The one coming out of B pointing down to D. You know anything about it?
Equal opposite direction.
Yeah, it's got to do the opposite of what it's doing on the other end because it's a two-force member. In fact, we know the magnitude, the direction, and the angle of it, and the units. Same kind of thing here for that force that goes over the A. We already know it. We know everything about it. We've got a couple other forces. We've got a force along this member, a force along that member, what else?
And a force down with 1,000 pounds.
You've got the load. Don't forget the load. It's very easy to be concentrating on the joint and forget that we've got part of our load right there, and that's got to go in. So that's 1,000. This is 1,500. This is 2,500. And then these are, this is BE, and this is BC. If you keep organized with it, much less likely to make a mistake. It only takes a sketch. Just don't hurry it, or you're just going to catch troubles for yourself. Do we know anything about the direction of BE and BC?
BC is an opposite direction of BA.
A little tough to say that for sure because we also have some sideways components here. We don't even know which direction that is. Do we know anything about this? If not, I mean, don't dwell on this too much because we can just put them in some way and get a minus sign in the answer if we're wrong. It's no big deal. But it helps you think about them a little bit. What?
BE has to go up
BE has to go up. Why is that?
because all the other forces are going down.
We've got two down forces, no up force. This is the only place we can get an up force. So it's got to go up. We think it doesn't matter anyway. If we are wrong, we just get a different answer.
So only 2 left forces. So we need to write 3 left forces.
And we've got that. We better put this one out there if we're going to get any balance on it. Now we can solve that. There's 2 unknowns, 2 equations, a little more complex just because it's got a bunch of extra numbers in it, but still 2 unknowns, 2 equations. Sum the forces in the 2 component directions. All right, when you do that, turns out that this is 5250. Again, remember all is in pounds. And this is in 3750.
too.
Cut. Chalk dust. I'm gonna have the equivalent of black lung disease miners get. I'm an old man, and you guys all come to my funeral and dance on my grave. All right, we keep going until we finish the problem. We've got 2 more joints to do, E and C. If you know any forces, you put them in. Let's see. We know that's got to be that way, and is 3 grand, because that was what was going on at the other end of it. We know that one's 3750, simply because that's what was going on at the other end of it. And so we have 1 left. Oh no, we have the reaction, but it's not unknown. We just darn well better include it. 10,000, and then the only unknown. We only have 1 unknown here, and that's the force EC itself. Do we know the direction of it? Why down? Because we already have some down and some up, so how do we know that one's down?
Seem a lot up.
Well, from sideways, we've got 2 that are going right. We need something coming left. That's the only place to get it, so it must go like that. And so you can double check that. It comes out to be 8750. Remember, try to assess the direction if you can, but don't make a big deal about it. It's really easy to get wrapped up in doing that when it's better to just put it in some way and keep going. Who wants to do joint C? Anybody volunteer? In a fit of generosity, I'll give you 15 seconds to do it. If you do it in 15 seconds, I'll pay you $1 million. And that's on tape. Can't use $1 million? Dana, I know you like to shop at the outlet stores up there. $1 million would go a long way at the outlet stores. 10 seconds left. 5 seconds. Oh, you guys just passed up $1 million. Let's see, we know there's a force there. We know there's a force there. What else do we know? We know the reaction force. We know we've got it backwards, so we'll go ahead and turn it around now. We know it's 7,000. What about the other 2? 15 seconds was generous. You could have done it that quick because we've got these forces already. There's nothing left to do. We're done. So that one goes down, this one must go up, and we already know their magnitude. We know their magnitude, their direction, and you suckers just passed up $1 million, just like that. See, back in my day, we could have used $1 million, but you guys are all so spoiled. All right, that should always happen. You should always get to the last joint and it's already done. Doesn't mean it wouldn't hurt to bring in one of these numbers and solve for the other one just to double check. You should get the same thing because don't forget, this 7,000 had an influence on the whole rest of the thing anyway. All these numbers are twined up with each other because they're all connected. And again, just my recommendation, but it's up to you. I think it makes a lot of sense to leave the layout very much the same. You're just so much less likely to make a mistake. Every one of these forces needs to be transferred to the next joint It's really hard to make a mistake when you do it this way. If you happen to come up with one intermediate solution, if one of these forces in here somewhere is a minus, you might do just as well leaving it like it is rather than flipping it around in the middle of the picture, because then you have two conflicting things in the picture and you may miss what's there. But that's kind of personal choice. All right, I'll set up a problem so that we can talk about it. It's a very simple problem, but there's lots to talk about when you're done. So I'm going to give you this one. This is your weekend work. We don't have time to finish it up here, so we'll just lay it out. So here's maybe a sign or something. There's a one member connected to the wall in our usual way, one rigid pinned joint and one roller joint. Then there's a horizontal member that comes off of that one, and two members here joined in the middle where a diagonal comes across. And then there's a load on the end. Okay, got the picture? A, B, C, D. I'll label these so it's easier for all of us when we talk about it on Monday. A, B, C, D. And the dimensions. Three meters and 3 meters. 5 meters across there and 5 meters across there. And then this piece, oh well, it just would fall out. That's 6 meters. Got the picture? Why is it important that there's a joint here, that there's two pieces? AC and CD are two different pieces. Why is that important?
So it wouldn't be a 2/4 member.
Otherwise it'd be a 3/4 member. It's got to be 2/4 members only. So we'll put a pin in there. Might not be the way you want to do it as a designer, but that's the way we're doing it here. All right, so do that over the weekend, just as practice, so I can get right to it on Monday and then do method of sections for the rest of Monday.